Hey, Benny. Looks like the no one's here yet.
Hello.
Can you hear? Hey, can you hear me okay?
Yes.
Okay, good. I know a couple of the other chairs can't go today, so I don't know if there's some bigger conflict. Hey, everybody. I give people another minute or so to join. Okay, I think we can go ahead and get started. I see Milos is here. Um, our agenda scheduled for Milos to present on attestation of location. So if you're ready to share, I think we can go ahead and get started.
Hey everybody. So it's a real pleasure to be here. Um, so if I understand correctly, you're suggesting that we dive right into the sovereignty certificates presentation, right?
Yeah, yeah, I think so. I mean, unless
Oh,
we have any pressing opens that somebody wants to get in, but I think, do you think your presentation will take an hour? Most of the time, I think we have lots of feedback, then can bring it a little bit longer.
I've scheduled the presentation to be maybe 25 minutes long,
Okay,
and then hopefully we can take some time for discussions afterwards, if that makes sense.
yeah, sounds great.
Okay, let me try to share my screen. Mm, okay. Oh, I will likely need to re-enter the meeting because I've just allowed Zoom to share my screen. So bear with me for a minute, okay?
Sure. Yeah, I guess while we're waiting, if people can put their names here in the attendees list on the Google Sheet.
Okay. Can you guys hear me and see my screen?
Yes.
Nice. So thanks for joining, and I'm really excited to have the opportunity to tell you what we've been working on and get your feedback. Before I dive in, I also need to kind of make an honest statement about where I'm coming from. So when it comes to the sovereignty certificates working group, my domain was mostly convening people to participate and provide feedback, and also around the location verification part, which is basically the location algorithms. My background is mostly there. So I'm saying this because there might be some questions that you guys have that are deeply technical around attestation or around some other parts of the specification that I may not be able to answer directly in this call, but I will take it with me and with the technical team and come back afterwards. That said, I'll do my best, of course, to respond to all the things that I can. So without any further ado, why I want to start with why sovereignty certificates, what is the motivation for this? So there were a couple of things that I think happened more or less at the same time. First of all, we had an AI diffusion rule that was rescinded, but now there are some signs that similar location verification technologies might be needed. And basically, we wanted to provide a solution for that. On the other hand side, in some other jurisdictions like EU and some other, there has been contractual residency scrutiny that's been expanded, and we feel that one way to consolidate in the future will be cryptographic evidence. So this is also an answer to that, I would say. And finally, there are a few, most notably the identity crisis, one variant, two type of attacks, where we interpret this as a consequence of the physical locations of TEs being treated as fungible, which is something that the specification that we have come to is basically trying to prevent this fungibility. So this is the first time that I'm attending one of these meetings. From my side, if you guys have any questions, feel free to interrupt me at any point in time. I'm okay with that, definitely. Of course, if you put your questions aside, that's good as well. We can do them afterwards. So an overview, we've started sometimes in Q4 last year. The idea would be to put together something of an industry-led group of people from chip manufacturers, from cloud providers, from networking companies, from CSPs, so that we can understand like the inputs that they have from different sides. The main contribution, I think, is the normative method, which is a network or ping-based location attestation that derives the location using the round trip times in between the known anchors within the network and the attested hardware. The normative data format, there is one EAT profile. Basically, the attester is signing the envelope, and then the verifier, as you will see afterwards, is signing a verifiable attestation result that is being presented either back to the attester or to the relaying party. And then there will be also words about the threat model, how we chose it, but in high level, we thought that this is one thing where the threat model needs to reflect the reality of today or tomorrow, where we want to convey trust between organizations that have very high level of resources and even maybe state level actors. But let's come to that. First, maybe let me also try to position sovereignty certificates to some of the other similar initiatives. The way we see it, or the way I see it, is there are a couple of axes. So there is vendor TE attestation, and then we have Intel PoE, which basically answers the question of who is owning the rack. And then we have like the NASR, which answers the question of the path. And we have a few initiatives that are located more closely to like the proximity and the location. So those are namely PTP attestation, VGAP, and SovCert. So putting those three aside, I still feel that they serve very specific different roles. When we talk about the VGAP, we talk about having specific sensors like mobile network operator sensors or satellite system sensors, and having sensor integrity as a trust anchor. On the other hand side, the PTP attestation is solving a different problem on a much more granular level of precision, but also on a much more smaller like scale in terms of distances and like more gated towards the local networks, if I'm interpreting this correctly. So the gap or the niche for sovereignty certificates is basically to have the round trip time as a sensor to the anchors that are not within the that don't have to be within where the attester sits. The trust anchors are the anchor honesty or the ownership of the anchors, anchor fleets, and then understanding physics, which I'll come to in a second. And then the thing why we would want to we could use this is that basically we can use different IP transport protocols, and as you will see afterwards in the next slide, in the trust compute base, what's inside, what's outside. Basically, it doesn't require you to trust the cloud service provider nor the host operating system. But let me come to that. The point of this slide is I feel that there is a specific niche for each of those each of those initiatives. Go ahead, Mark.
So have you validated with any of your customers that not trusting the provider to tell you where the server is located is a requirement?
Okay, that's a very good question. We have, in a sense, that, for example, you have U.S. Cloud Act that is asking the US-based cloud providers to provide back the information that they have to their to the US government. Then there are specific initiatives, sovereignty initiatives, where the cloud trust is something that's not assumed. And then I feel that there is also, speaking to a lot of very sensitive workloads, it seems that still there is about like 50 or 60% of the load that is being held on-prem, and that this a part of this load with this specific or something like this could actually become a load that is being executed within the cloud environment within this new regime, if that makes
You're
sense.
saying that a customer, like, and again, the reason I'm asking, I work for a large regulated customer and we operate worldwide.
Mm-hmm.
We recently looked into basically light speed validation of locations. This at this point is more of a research project, but we started asking questions like, are we going to have to put a sensor on every server, of which there are quite many, right? And ultimately, even that comes down to there can be maybe one uh, verified source of truth that in a data center that says, well, I'm really really here, right, because of the technique you just mentioned, light speed, and but then every other server pretty much have to take you know it's not going to be independently also certifying its own location. It's going to basically take a claim from that. At least that's my understanding of how the current technology works. So again, are you telling me that there are customers who are so concerned about this that without this, I don't know, relativity-based space age technology, they're not going to move their workloads into a data center if the data center were to tell them, look, we'll have a contractual obligation with you that we will, in fact, keep track of which jurisdiction each server is on, and we'll just give you that as a claim. Like, you're really saying that the trust is so low that they would never that they would keep a workload on premise in even if such a guarantee could be given.
Look, in all honesty, I can't make this claim. I had a number of conversations, and this is what the landscape look like to me. As Lucid, we have signed a contract with a government of a EU government to work on one of these systems, for example.
Right,
So my position is that the market is or will be there. I feel that the
right.
trends are going in that direction, that there will be no assumed trust to the
Hmm.
hyperscalers. So
Right.
that's kind of my position. That said, I might be wrong.
Yeah. Well, so if I were to fast forward mentally in terms of how you would pull such a thing off, we currently have multi-testers, right? Complex testers, so CPU plus GPU plus
Mhm.
SmartNIC, which is your typical cloud workload, is not just, one trusted execution environment. So ultimately, I would imagine that location sensor or a source of truth about a location is sort of one of these multi-tester components that would feed into the the entirety of evidence that an attester presents to the verifier. Is that how you also see this?
So yes, if I understood correctly, so there is like a composite environment where you have CPUs and GPUs and smart NICs, and everybody is an attester here, and then those attesters. One thing that is not here that we're also working on is like a node that we are working on that's kind of putting a composite claim on the entire environment. But when it comes to sovereignty certificates, yes, it basically attests to each of these
But
components being
ultimately,
a
it comes
specific.
down to one of the sources of evidence. I may not be using the right terminology here. In a multi-attester, just
Mhm.
gives you this claim, perhaps a signed claim, saying I'm in Frankfurt, right?
Yeah,
And that effectively it percolates up to the verifier as part of a bundle, saying what else is this workload claiming about where it's executing, right? And then what comes back is attestation results that include your location as a claim, which effectively plugs you into the entire protocol stack above.
yeah, yeah.
Okay, all right, thank you.
You're welcome. Thank you. Okay.
So I have a question as well.
Hi, Mohammed. Go
So
ahead.
yeah, hi. So I'm trying to understand the overall spectrum and the overall terminology and technology. So one thing I would like to understand is who is actually the provider of this whole thing, that location, basically that you are claiming about. So who is really, isn't it the cloud service provider? Like who you really have to trust in order to get that claim? That's my main question. And secondly, talking about the uh, like one of the examples that Mark was just giving was that, okay, so the server is in Frankfurt. The verifier also needs that information in order to check that it's really in Frankfurt. So my question is twofold, like one from the tester side, who is one that is generating that claim? And how is it possible that the cloud service provider itself is out of the TCP and you still get that reliable location that it's really in Frankfurt and is not in Berlin and is not in Dresden and so on? And the
Mhm.
other side, from the verifier side, how does the verifier get to know that, hey, I have got some kind of a claim that it's in Frankfurt? How does the verifier get to attest, not attest, sorry, how does the verifier get to appraise that it's really in Frankfurt and is not in Berlin, it's not in Dresden? That's twofold question. Thanks.
Okay. Thank you. So what I propose we do is I go forward with the slides because all of those questions I feel are more or less answered in the following slides. And then after the few slides, I can come back if there is something missing. Okay?
So maybe you can answer in terms of this slide first, because you are mentioning here trust anchor. That's what my question was like kind of focusing on. If you think that other slides are better, then it's fine. We can proceed.
Yeah, yeah. There are slides like the next one
Okay,
is
okay.
specifically about like the trust compute base. So the idea here is that we don't want to trust the network, we don't want to trust the host operating system, nor the hypervisor, nor the cloud provider. The idea would be to trust just the silicon of the attester, and then the micronode. The idea again is to understand that the round trip time is bounded by the speed of light, and to use that as a method to have a very low granularity understanding of location. Go ahead.
Okay, so I now see an answer to my question. Thanks very much for this slide. So you are claiming that the cloud provider remains out of the TCP, it's hostile, right? So
Mhm.
going back to my question, now if I am the cloud provider, I am hostile. Instead of putting the location of Frankfurt, I put in the location of Dresden. So how do you ensure that whatever I'm putting inside it, so you are saying you are only trusting the hardware root of trust silicon. Silicon doesn't know where it is, right? So it can be I could take that server, put it in my car, and take it over from Frankfurt to Dresden. How does the silicon know that it's in Dresden or Frankfurt? Same applies to T microcode. So I see that this is I
But
don't
Mohammed,
really I don't really follow this.
he didn't yet present this, right? We are not
Usama,
at that
I
point.
really appreciate your eagerness to understand this. I urge that we go to the following slides. I think I have more or less everything ready for you, if that's okay with you.
Okay, sure. I was just not understanding this slide. Thanks.
Yeah,
Please
yeah,
proceed.
yeah. Thank you so much. So I think you guys know much more about this than I do in terms of the RATS architecture, normal roles, attester, verifier, endorser, and relaying party. The one thing that is key that we've introduced here is something that we call an anchor. Anchor is basically a confidential compute capable server that is put in a location that is fixed, that we can trust, and that has a specific level of security, let's say tier 3 plus data center and so on. So here's maybe where I want to spend a bit more time, and hopefully this will land well. I'll go through how a verification cycle plays out, and then maybe Usama, you can see if this answers your question, or we need to spend some more time on it. First of all, like the endorser is a component that has referent like golden standards of the attesters TCBs and the measurement of the TCB, but also it knows the directory of all the anchors, so all the fixed points around the world, let's say. The sequence starts with the attester initiating the sequence and basically pulling out like an ephemeral key pair on its side and pinging the verifier. The verifier responds with the nonce and the signed directory of all the anchors that it got out of band from the endorser. Then what happens is that a tester calculates the hash of the ephemeral key and the nonce and puts it in the report data field. Together with its TCB measurement, they form the quote, and this quote is signed by the hardware root of trust. So then a tester basically probes the anchors. The anchors return the signed receipt, so the timestamps and the nonce echo and their own ID, the anchor ID. The round trip time is computed on the side of the attester, basically because the attester knows when it sent out the probe to the anchor and when it came back. And then the attester basically puts together the entire envelope that is ephemerally key signed by its private ephemeral key and send back to the verifier. Now, the verifier uses the public ephemeral key to validate that the envelope is okay. Then it uses the root certificates from the endorser to validate that the platform quote is okay, so that this hasn't been tampered with. And then it compares basically the TCB against the golden references that were obtained by from the endorser. The endorser verifier dichotomy is there to kind of split the responsibilities or the ownership, so to have a sort of a federated way of governing the entire specification. Then verifier recomputes the hash of the ephemeral key and the nonce, and it compares it to what it got through the report data field. If it's okay, then it uses the anchor's public keys to validate the receipts that it got within the envelope. This is used to prevent the replay attacks. And finally, when everything checks out in the previous steps, then it uses the location determination algorithm to understand the position. At this point in time, the location verification algorithm is just, and you will see this also in a slide afterwards, it's just bounding. So it's like understanding the speed of light and the time gives you a circle around each of the each of the anchors. And then basically in the intersection of those circles, you get a specific polygon. And then a circle around that polygon is where we claim the location is. We evaluate this against the policy, and then if it passes a specific policy, then a bar is minted, and depending on if it's a passport mode or background mode, it's sent to either the relaying party or the attester. Okay, I'll pause here. I think I've maybe Usama, if this helps a bit. Go ahead.
Right, thank you. I think this was quite helpful, and I get an overall idea of what the overall picture is. So let me try to summarize my understanding of the assumptions that you have, if you don't mind. Is that fine for you?
Of course.
Okay. So my first assumption or understanding is that, first of all, anchor that you have NX or XN, whatever that means. So basically, that is trusted by the verifier, by the relying party, and by the attester. Is it correct? If you go back to that slide, please.
Okay.
So this anchor thing, that this is trusted by attester, verifier, and relying party. Is my understanding correct?
It is trusted, but if I understand correctly, it is trusted because the each anchor is again a confidential compute capable server. So the receipts that the anchors are providing are signed with the anchor public with the anchor private keys, and then the anchor public key is given to the verifier by the endorser. So that's the way how I feel we trust the anchors, if that makes sense.
Let me put it maybe more simply. So you're saying that somehow, we will go into detail of how that somehow happens. Somehow the verifier has authentic public key of the anchor. Is it a correct summary of that thing?
The verifier gets, so I think your question comes back to how the verifier trusts the endorser and how the endorser gets to the public keys of anchors.
Okay, so you are saying that the verifier gets the public key of anchor from the endorser,
Yes,
correct?
endorser is basically the architecture
okay.
role where we have put the golden standards for the TCB measurements, and then also like all the directory and references of the anchors, including the keys.
Okay, so now I have better understanding. So endorser in the RATS architecture is already trusted. That's fine. So you are saying that somehow the public key of the anchor is also added in that endorser. And since the verifier already trusts that endorser, that can get that public key of the anchors, all the anchors from the endorser, correct? So far, am I on
Yes.
the same page? Okay,
Yeah.
very good. So now, okay, we have this thing now solved out. And what I now want to understand is you didn't talk about this TLS 1.3, which is quite interesting for me. I'm trying to understand in 7 steps that you explained, where does this happen relative to all of these 7 steps? Where is the TLS connection actually established?
So it's established, as far as I understand, it's established in the first step when the attester is initiating this to the cycle, the attestation cycle. It is using a TLS 1.3. That is what specification is saying.
Okay,
And
fine.
I
So you
think
have
it's used
post handshake.
yeah, and I think it's used then throughout basically the cycle, but it's starting with the first initiation.
I see. I just wanted to understand when the attestation thing is going to happen. Like, oh, so you have TLS connection established, and then the attester or the verifier initiates something on top of that established TLS connection. And then they exchange all these things, evidence and the nonce and all these things happen on
Yes.
top of an established. Okay. So you have in simple words, you have basically, we have discussed a lot in this SIG, like you have post handshake attestation, which is actually good. That's avoids a lot of attacks. So that's nice. And my third question then is if you can elaborate a little bit more about this attester and anchor thing. I'm thinking about like verifier kind of trusts this anchor, that's fine. But what if it happens that the attester forwards it to somebody and that somebody is actually kind of, I'm thinking something like a relay attack here. And how do you kind of avoid that relay attack in this case, that attester is forwarding something to somebody and it's increasing the time of the whole attestation procedure? And it could be the case that I actually could forward it to a malicious party and so on. So can you kind of
Yes,
explain on these
I
lines?
also have a slide on
Okay,
that
okay.
one, if that's
Thanks.
okay.
Then I'm
Thank
done.
you.
Yeah, sure. Thank you.
Hank, you wanted to say something as well.
Yeah,
At
but
one
I
point.
forgot my comment. Yeah, I think the inputs to the verifier were you compose, I think, intuitively endorsements and reference values with the endorser. I think, but I think also that arrow tells me that. So I think that you're just simplifying what endorser gives the verifier. And
Yeah,
sorry
the
for
arrows
not.
here are just, sorry, the arrows may not be very representative here of the actual communication is basically flows in two direction. But I'm sorry, have I missed a specific question here?
My question, I think, was that reference values are not endorsed. So that's a interesting conundrum. Only things that cannot be produced by the attester, but about the attester are endorsed, except, of course, the reference values. Those are not endorsed, but are asserted by a trusted third party. And if the difference is not clear, I think we have to do a cycle here at some point.
Sorry, I may have lost a bit in communication, but if I understand correctly, you're saying there is a conundrum because the references meaning.
Yeah, I'm a train.
Oh, okay, no worries. The references meaning like the RTT measurement are not coming from the endorser rather than the anchors. Is that like the conundrum that you're describing?
Yeah, it is a measurement. It is not coming from the endorser, correct?
Yeah,
So that is something that is not just counterintuitive, but endorsements are all the things that the attester cannot tell you, but that are about the attester.
Yes, I agree that it's maybe a bit different than the typical, I would say, architecture. The reason for that is
Okay.
yeah, let me go a few slides forward and then towards the end
Sure.
I'll make sure to try to address this one as well. Okay. I think we can move to the next slide. So there are a lot of shells for each of the roles, but I put out just a few to kind of give you the stranger ones in a way. So the attester on one hand side is choosing from the entire directory of the anchors. It should be geographically aware that the closest ones carry the most location information, and the ones that are basically not all in the same azimuth or in the same direction. So this is an algorithm that should prioritize how the anchor geometry is being chosen. It goes to serve the precision of the final result. And then I think maybe, yeah, the endorser, I think we've touched on this. We would need to draft some sort of quorum extension, or we've drafted a quorum extension for this so that we have a standardized way to have the anchor directory. So this is going back to the previous question. And then in the interest of time, I'm just gonna move forward, and because there are a lot of things, and I see now that we have maybe 18 minutes left. So my view of why this is a technical contribution is because I feel that this is something that is having a threat model that is fairly hostile. So we don't trust the sensors, we don't trust the host, the hypervisor, and so on. We do trust only the physical boundaries, so the speed of light in a specific transmission medium, or basically full speed of light. We can do with both. And then we get, as you will see a bit later, we get to a precision that is not very high. We get to 100-kilometer precision, but our claims are jurisdiction-based, jurisdiction-level claims. And these claims are, for regulatory purposes, oftentimes enough. And then there are like a couple of research directions. We call them track A and track B. Track A are the ones that basically preserve the 100% confidence that the attester is 100%. Confidence that the attester is within a specific location bound. And then track B are the ones that kind of trade on the stated confidence for a much tighter bound or a much tighter resolution. And we can, if time permits, we can talk more about what we are seeing there. So this is one specific example. Maybe I should have put this somewhere earlier. Like the green star is the actual location. The blue antennas and the green antennas are anchors, and then the red target is the actual calculated location that we have. This is an example from Europe, where we have put the network of our we call them landmark endorser servers, but basically the anchors. And this is like the red polygon is actually the polygon that is being obtained just by using the speed of light as the limit. So you can see that the size of the polygon is really big. You can see that it spreads multiple countries, but still you can say that specific devices within European Union, without trusting basically anything else but the speed of light and the TCB that we've mentioned previously. So a few more words on what we have measured so far with the test beds that we have put. The distance errors are related usually in between 50 and 300 kilometers on using the private fiber transit networks. The things that I've mentioned previously, so the spatial distribution of the anchors matters. The closer anchors carry more information, which feels normal, because when you go further away, then the actual path and the latency of the hops and the time that the signal goes through servers and so on, it compounds. So the actual bound goes much wider than where the actual attester is. So there is less information, location information in those measurements. There are other things that we are working on right now, and some preliminary measurements, they suggest that we can get to like tens of kilometers uncertainty under a specifically defined anchor density and transit conditions. So this is something that we are documenting right now, and I hope in due time we'll be able to share more. I think we've covered more or less this. So there are two trust tracks. On one hand side, there is the hardware trust track, which starts with the root CA, and then it's being included in the quote, and then in the envelope. On the other hand side, there is endorser trust track, which is also then through anchors and included in the envelope. I think this is another way to represent what we've discussed at large in the previous slide, so I'll not go in depth at this one. What I want to touch base before we conclude is we call this the AI passport. It's something that we feel has a brandable name, but I'm not 100% sure with it. It's basically a relaying party name for a verifiable attestation result that is signed by a verifier. And we call it the AI passport. It includes the EAT profile. It includes the time. One thing that I forgot is like the expiry time is basically set typically to 10 minutes, which is something that we have envisioned in the specification. You can see the location claim has longitude and latitude and specific radius of the encompassing circle, and then a confidence level, and then specific policy IDs that have been passed and that can be issued. And this is like a specific typical RFC 9711 profile, EAT, standard, more or less standard things as far as I know. Finally, the current status specific to Lucid. We've developed the attester, which we call the Lucid agent, the anchor, which we call the landmark endorser server, which is a bit confusing having in mind the endorser as we've spoke about. And then we've developed a component that is called a control plane, a verifier. The most, I would say, challenging thing for the technical team was the Lucid agent. I think it was built in Rust. Basically, they've needed to work to very deeply to get to a very specific understanding of the timing and propagation from different OSI layers and stack. We've tried this with NVIDIA Confidential Computing, AMD, on Nitro enclaves. We have also some of the anchors on GCP. We've done this through different cloud providers. Now we have more than 10 anchors with confidential compute deployments, and I would say months of round trip time measurements. 2 proofs of concept so far going on. We have some conformances gaps, but like I think it's nothing out of the ordinary. So with that, I think I wanna pause. I think I've come to the end of the slides, and I want to open the floor for any remaining questions. Thank you.
Yeah, thank you. I think we do have some hands up.
Yeah, I just want one question regarding you did mention said attestation result structure, but in the evidence, is there a receipts? What is the structure of your receipts coming from the anchor, and does it get into the evidence?
So if I understand correctly, you're asking if the evidence that is presented to the relaying party
verifier.
or giving back to the
No,
verifier, or to this is the sorry, this is
no,
the
this is the attestation results. But going back to your original slide deck where you had the architecture diagram where the receipts get from the yeah, this one, yes. So if I understand correctly, the anchors report some receipts to the attester, right? Then which then some way gets presented to the verifier, which I'm not very sure what exactly gets presented to the verifier as an evidence. So is there a structure of your evidence?
I don't have it here in the deck. I'm happy to follow up with a specific structure. The way how I see this structure is that there is this envelope of things that includes the platform quote. So the entire envelope is first validated by the public key, ephemeral public key of the attester. So we know it's the attester, and then within that we have like the platform quote, which is validated by the root certificates, and compared. Then we also compare this TCB to the golden references that we got from the endorsers. And then in the report data field, it has the report data field, which is basically which is validated by recomputing the hash of the ephemeral key and the nonce. And then we have the set of receipts from each of the anchors, okay? And
okay.
the verifier has the public key of the anchors, so it can validate each of the receipts. So this is in general the structure of it. If you're referring to like a specific code,
Okay.
I can provide that.
Okay, no, I was interested. That's pretty much answers. So effectively, receipts do travel all the way up to the verifier.
Yes. Yes.
Yeah. Okay. Thanks.
Thanks. I see Giri or Jiri raised their hand, and then Mohammed Usama as well. Who wants to go first, guys?
I would actually say Benny raised his hand, so I'm waiting for him to, maybe he wants to go first.
It's not so important, but my questions are not about the attestation side per se, right? Sure, important details, but for me, this is a solvable problem, I would say. For me, the question would more be about really how fine can granular is the location, for example, right? You showed example on your last slide, right? So that was pretty perfect. But did you do experiments with anchors all across the world using multiple measurements or whatever, right? So because I guess at the end of the day, it would be as closer you can find the location, the better, right?
Yeah. So this is what I'm very passionate about. Yes, we did. I did like without signatures and everything, but like I've used some data to simulate the measurements from like 200 locations across the world. And what happens typically is that once you start adding the locations that are further and further away, the polygon just remains the same. It doesn't shrink anymore. And the way how we are thinking about it, or I'm thinking about it right now, is introducing a very close, when you have a closer And I can't speak to it yet because it's not fully validated, but I'm just going to hint towards the way how I'm thinking about it. If you have an anchor that is very close to the attester, then you can use it to actually abstract part of the latency for some of the other anchors and get the improvement in the actual positioning algorithm. Now, positioning algorithm aside, I think like the mechanism of the specification is what we want to be very robust. And then now I will continue working on some of these specific location determination mechanisms that will hopefully allow us to get to a few tens of kilometers of distance error with confidence level that are still pretty close to one. This is where I'm aiming to go.
Yeah, it makes sense. But for me, it's also obviously an IP. The routing is very. It can be long, it can be short, right? You don't know. It might make satellite hop, and then you're screwed, basically, right? So, so did you experiment just using one anchor, but using the same anchor 10 times? Because even that might lead to different results,
not
right?
only 10 times, but weeks. Weeks, and that's where we get like one axis of improvement is basically understanding the space, the time the differences, and using multiple measurements. But when we go to private fiber, we see that the consistency is pretty high. This is the overarching thing that we've seen from months of measurements. That it goes through a satellite, it doesn't happen for like megaport private fibers. It doesn't happen that much for the AWS private connections and so
on. And only one hint, a colleague just wrote me that, but it's just when you present this technology here, right? I think the main trick you're using is, right, you can delay the connection, but you can't shorten it, right? That is the main thing underlying.
Yeah.
And maybe next time start with that. I guess that would.
Thank you so much. The point is like, if you can delay it, but by delaying it, you're not going to pass the policy check. You're just going to fail it.
Yeah, so but that's it. Sorry for all my questions. Please.
No, thank you so much. Thank you so much. We have a few more hands.
Giri, right. So, Giri, you want to go first?
Sure. I'll just, I think I'll try to be quick. Okay, first off, a little history. When I added the location feature to RFC 9711, at that time, I was dealing with handheld devices and with rather sophisticated location engines and a trusted path to those location engines. So that was it took those were engines that took a lot more than just GPS as part of their input into into coming up with a latitude and longitude. Obviously, in data center, that's not going to those kind of assumptions are not really applicable. I think though, what I was hoping to get out of your presentation, going back to Mark's original comments at the beginning, I'm still not really clear on here, and particularly when I look at it from you said you had implemented this attester on S&P. So when I look at it from that perspective, right now, a lot of roots of trust that are provided by the silicon vendor, like if you're familiar with Calyptra, they have features such as PKI transfer, where the CSP can actually provide their own endorsement, and that can provide an implicit trusted location endorsement as well, which I believe Mark kind of mentioned at the beginning of the call. And I think the model you presented here has rejected that and excluded the CSP from providing any trusted endorsements. What I don't understand, though, is the Lucid attester built on S&P. I don't know why its location assertions are any more valid than a CSP's, because it is just it's acting as a guest on S&P, which means that it's a confidential computing guest. It has there's a guarantee that its memory is protected, but there's no guarantee on the integrity of the anchors it's using to form its estimates. There's no guarantee on the integrity of the source code it's using to implement the attester. So I'm wondering why Lucid considers that a more trustworthy model than the CSP endorsement. That's uh, okay. Thank you. And thank you
Yeah.
for this presentation too. It was very informative.
Thank you, Jerry. So this is a very good question. I'll try to respond to the best of my knowledge. I am aware of OCP Calyptra, but not in great details. What I can tell you about how we look at it is still going back to like the trust compute base that it excludes everything on the hypervisor, on the host side, on the cloud side. So the idea for the actual attester software is to be open sourced, so the actual customer can understand what's happening there. And then when it comes to the actual endorsers and the verifiers, the idea there is to be governed in a federated way, so that you don't, in the end, you don't need to trust Lucid as a sole. Like in the end, our idea would be that we call this independent location verification provider, ILVP, something like that. The idea would be that you have a market of these, and then you could basically plug and play one of those, and in the end, without having to trust them as much as well, if that makes sense.
Thank you.
Thank
Okay,
you.
so very quickly,
Mhm.
yeah. So I was just to say in very short words, I was not convinced that out of TCP applies. I have put my paper in the chat. Basically, there are attacks that are still applicable. The identity crisis, that's the threat model you showed doesn't apply at all. Because the threats we show there still apply. You have more threats in the sense that I think somebody was pointing, I'm not sure, it was Benny probably was pointing already that it depends a lot on what path is actually taken from the attester to the anchor in order to estimate that value, right? And so it's all that routing and which path is playing a lot of role here. And in addition to that, there is the possibility that it could go through something which you also need to trust in that case. And my third comment would be, what would be the evidence format that, let's say I'm thinking about, let's say Intel TDX, like it has CPU hardware, PCE, TD coding enclave, TDX module, trust domain on top. So this is that hierarchy. So, and it generates an evidence accordingly. Is there a need to change anything in that evidence format, or what you called as something? I think you showed some big box in one of your slides, which was, what did you call it? Some composition or something like that, but I didn't follow. That is additional to that evidence TD like code. You will add something, append something in composition to that, is probably something like that. So that part would be nice to clarify a little bit more, maybe by email or something afterwards.
Okay, so I need to make sure I understood the question correctly. I understood the first part, that you're not convinced that this structure is a good response for the identity crisis types of attack, B types of attack. But then,
Right.
if I understand correctly, the second part was basically to provide more details on this structure, or something else. Sorry, I didn't understand quite where you were aiming with this.
No problem. Sorry if my question was unclear. So uh, let's say let's say we have TD code, like let's say you have Intel trust domain extensions. Your TE is now, your attester has TDX, and TDX will typically generate TD code. Like, my question is, does your proposal need to change something? The slide that you are showing, does it need to change something in TDX, or is this somehow orthogonal to that? And if you go to one of the slides, you had something coming from two tops and then this envelope. So is this envelope what the code here will be the TDX code, or does the TDX code need to change? That's my question, maybe in short terms, and then we
Okay.
will follow up later.
The way how I understand, basically this is a TDX in that specific example. This would be the TDX quote, and then it assumes the specific report data fields and the TCB measurements that are inside it, if that makes sense.
Right, maybe a binary answer to my question. Does TDX report in your proposal need to change or not? The rest we can follow up later on.
I
Does
think
the
it's
TDX code?
he does mention report data. That would be the linkage.
Okay, so report data changes.
We're way over time. So
Okay, sure. Yeah, thanks.
say thank you, Milos.
We can follow up on this. I'm happy to kind of dive deeper in this afterwards.
Sure, I will reach out to you. Thanks.
Thank you.
Very interesting.
Thanks a lot, Milos.
Thank you guys so much. I enjoyed your company and I enjoyed the questions very much. Any comments, any contributions that you want to make? You have a link here, and feel free to reach out to me, milos@lucidcomputing.ai or info@lucidcomputing, and I hope that we can get some comments, and I would be happy to get additional feedback.
All right. Thank you.
Thanks.
Thanks. Bye.
Bye.